So good afternoon everyone, good evening everyone. So in today's class that is week 5, we'll be covering topic of subsurface water. So in this class we'll talk about how water gets infiltrated and how water travels from subsurface flow to that is from unsaturated zone to saturated zone, and we'll also study about the process of infiltration in detail. We'll derive to one equation which is very famous equation of 1D unsaturated flow called as Richard equation. Then followed by that we'll study about how we can measure infiltration using experimental approach, that is single ring or double ring infiltrometer, and also we'll see study about the estimations of infiltration using various equations, empirical equations such as Horton's equations, Kostiakov's equation, Phillips equation, and we'll conclude the session by deriving another equations called as Green-Ampt equation. And also in the second part we'll study, as usually we do in this session, at the end we'll discuss the numerical based on the theory, and at the later stage we'll also discuss few questions based on the assignment 5. Right, so we'll start with the process with the topic which is subsurface water. So in the previous class we have studied about atmospheric water. Inside atmospheric water we have studied about precipitation, we have studied about evaporation, we have studied about evapotranspiration, right? So in today's class we'll study only about subsurface water. So what happens when the rainfall occurs, like some part of it is stored on the vegetation, and that is called as interception storage, right? And after this what happens is some part of the water will rainfall will flows on the ground surface, which is known as surface runoff, which we will be covering in next week. And the today's topic is after like some of the part of water is flown on the ground surface, the remaining part, what happens, it will go into the ground, and that process is called as infiltration. So in subsurface water we'll study about the process of infiltration. So let us see like how the infiltrated waters get converted to. So the infiltrated waters will convert obviously to soil moisture, that is the first topmost layer below the ground surface. And after that you will get two zones. The two zones are nothing but unsaturated zone, and another is called as saturated zone, right? So unsaturated zone means what? When we look into a soil profile, we'll see like there are three different layers in soil profile, and those layers are nothing but solid particles, then there is a water body like water, and there is air. So in unsaturated zone what happens is the soil is not completely, the void of soil is not completely filled with water. So that kind of soil is called as unsaturated. But when we look into saturated, it means the void is completely filled with water. So the soil profile will only have two things, that is it will have soil, solid particle, and it will have water. Now look into this groundwater table. What effect does it has? So what happens is usually when water starts infiltrating from the ground surface, the first zone that will cover is called as subsurface flow, and that zone is called as unsaturated zone. So we already know what is unsaturated zone now. So the water which is there between below ground surface and above water table, that zone is called as unsaturated zone, and the water which is present, which is flowing between this zone, is known as interflow. So interflow is that water which is flowing in the unsaturated zone, that is between ground surface and water table. What happens after this process is the water will start infiltrating or percolating in below the water table, and that is when the water enters the groundwater zone, and that is also known as saturated zone. So here the water will also move, and this groundwater flow, the movement is known as, the flow of water is known as base flow. So there are two types of flow, interflow and base flow. So interflow is the flow of water which occurs in unsaturated zone, and base flow is the flow of water which occurs in groundwater flow, or like groundwater zone, or we can call it as saturated zone. Now this is what I was talking about, like how a soil profile looks like. So when you look into a soil, you'll usually have three particles, like three zones into it. The first is called as solid particle. This thing is called as solid particles. Then other is called as void, and the void is consisting of two things, air as well as water. So whenever a soil, in any soil, if the void is completely filled with water, that kind of soil is called as saturated soil. And if when we talk about an unsaturated soil, it means there will be presence of all the three things, that is air, water and solid. Now there is an important definition to be discussed here, that is called as porosity. Now porosity means what? Porosity will give you the total volume of void which is present in the soil sample. So total, when we talk about void, it means air as well as water. So porosity will give us the volume of air plus volume of water divided by total volume of soil sample. So that definition is really important, porosity, because we are going to relate porosity and moisture content in the upcoming part. The next definition is moisture content. So moisture content will give us the volume of water which is there in the volume of soil. So if we look into this diagram, if we only consider a volume of water with respect to total volume of soil, it will give us moisture content, which is represented using theta here. And the other definition was porosity. Porosity means volume of both the water and air voids. It means total void with respect to total volume of soil. So that will give us porosity. So these two definitions are really important, porosity and moisture content. Now let us see here what is defining pore space. So the maximum, we need to know like what is the maximum value one can have of porosity as well as. So when we look into dry soil, so for dry soil the theta is equals to 0, right? Because this volume is the volume of water will be 0, we can say that the moisture content will be 0 for dry soil. But when we look into saturated soil means the volume of void is completely filled with water only. There is no air space inside the soil. So in that case we can say that the porosity will be equal to moisture content. So the maximum value of moisture content that the soil can have is, it will be 0 for dry soil, and max n for wet soil or saturated soil it will be equal to its porosity. So this is the range of moisture content from 0 to porosity. 0 when the soil is dry and porosity when the soil is completely saturated. Now another thing to remember here is like how the energy for flow through porous media, like what are the total energy available in a soil moisture. So we can say that the total energy, this we have studied in fluid mechanics class also, right? So the total energy is divided into three subheading. So those are suction head, datum head and kinetic head. But if we talk about unsaturated flow, in the unsaturated flow what happens is the velocity head, the velocity is very slow, is very less, so we can neglect this term. So the only thing that will be left is psi plus z, that is suction head plus datum head. So we can say that the total energy is nothing but sum of suction head plus datum head. So here they are saying in the unsaturated flow the velocity of flow is very less in comparison with datum head and suction head, so we can neglect it. So we can say that the energy which is causing the flow in unsaturated medium is due to suction head and datum head. So just remember this equation. This will be needed when we will be deriving 1D unsaturated flow equation, that is Richards equation. Now let us see like what is the 1D unsaturated flow equation consist of. So just look at this figure. So the 1D unsaturated flow equation, it relies on the principle of continuity equation and momentum equation. And again, as in the previous class we have used Reynolds transform theorem to derive equations, right? Here also we are going to use Reynolds transform theorem. We are going to apply it for the continuity equation as well as for momentum equation, and then we are going to add both the derived equation, and that will give us the 1D unsaturated flow equation. This is a very renowned equation. This equation is also known as Richards equation. So what we are going to do is we are going to just derive this equation now. So we are going to derive the equation which is 1D unsteady unsaturated flow. So let us consider a volume first. So consider a volume of sides dx, dy and dz. So we have a volume of soil here. This is dz, right? And let us assume the moisture content. So the moisture content we know it is denoted by theta. So let moisture content equals to theta. And now we can calculate the volume also, the volume of total soil. So the volume of total soil would be multiplication of all the sides, that is dx, dy and dz. So we know the volume of soil, we know the moisture content. So based on these two things and based on the definition of moisture content, that is volume of water to the total volume of sample, we can calculate the volume of water now. So in order to calculate the volume of water, we should rely on the definition of moisture content. So moisture content is nothing but volume of water divided by total volume, right? So based on this we can calculate volume of water. It would be theta times volume, and the volume here is dx, dy, dz. So this is nothing but volume of water. Also we can use of Darcy's equation or Darcy's flux, which give us the volume of flow rate per unit area. So this is the equation of Darcy's flux, which give us how much amount of water is going to travel per unit area, or how much discharge of water is going to travel per unit area. Now what we are going to do is, these are nothing but the assumptions what we are going to do. Now we are going to apply RTT and derive continuity equation, because the 1D unsaturated flow is nothing but combination of continuity equation as well as momentum equation. So first we are applying RTT to the continuity equation, right? So whenever we use RTT equation, what we do, the first thing we consider is an extensive property, right? An extensive property for what? We are using conservation of mass. So obviously the extensive property would be mass here, M. Mass of what? Mass of soil water. The next thing is, once you know extensive property, next thing is we can derive intensive property, which is nothing but extensive property per unit mass. So here the extensive property is mass and we are going to divide it by mass, so the intensive property would become 1. And also we know that as per law of conservation of mass, we know that dm by dt is equals to 0, which means dB by dt, the term which comes on the left hand side of RTT equation, would be 0. These things we have already derived in the previous class also, but this is just a revision for you, right? So now what we are going to do, we are just going to substitute all these things in our RTT equation. So what is the RTT equation? The RTT equation is nothing but dB by dt is equals to rate of change of with respect to time under controlled volume, intensive property rho dV, right? This is the first term, plus second term is for control surface, internal property rho v d of dA, right? Now we know that the left hand side term, that is dB by dt, is 0 here. We also know that beta, that is intensive property, is 1. So instead of beta we are going to write it as 1. So this will become rho dV and this will become rho v dA of dy. So let us name this equation as equation 1, right? Now what we are going to do is, we are going to look into first term in detail and then we are going to look into second term detail. So what we are going to do is, we are going to just look into first term and then later we'll use the second term. So let us look into first term now. So if we look at the first term is nothing but d of dt rho of dV, right? So here what is dV? dV is nothing but the volume of water, which we know. What is volume of water here? It is theta times the volume, right? So what we can do is, we can write dB by dt, and we are taking triple integral, so this will become rho w. Instead of d, rho becomes rho of w, and volume will become theta times of dx, dy and dz, right? Now what we are going to do, we are just going to take the constant outside. The constants here are density of water and the dimension of solid. The what is going to change? Only moisture content changes, right? So we can write this as rho w dx dy dz into d theta of right? Let us name this equation as equation 2. Now let us look into the second term. This is all about first term, right? This is first term. Now let us look into second term. So the second term is nothing but it gives us the inflow, that is the volume of water which is entering. So if you look at it into the base diagram, main diagram here, so the inflow is nothing but here, the volume of water which is entering from here. So the volume of water which is entering from here would be q times of dx dy, right? So here u is nothing but q times of dx dy, and at the same time outflow is whatever volume of water is going to come out of the other side. So that is inflow term, that is q of dx dy. This is the inflow plus rate of change of water with respect to dz, right? This is the outflow. Now if we want to look into total volume or net volume, so that the net volume would become, so here comes our second term, that is d double integral of control volume rho v of dA is equals to net outflow. So the net outflow would be, like, we need to subtract this from this, so the net outflow will become rho w dx by dy by dz into dq by dz, and this is nothing but our equation 3. Now if we look at equation 2 and equation 3, we can substitute equation 2, 3 in equation 1. So we are going to substitute equation 2 and 3 in equation 1. In 1. So what we'll get, the left hand term was 0, the right hand term was, but we can simply arrange this term and we'll get the final. We know this thing, these terms are constant in both the equation, right? If you look here, these two terms are constant in both the equations, so we can simply cancel both the equations, both the terms, and whatever is left is the final equation. dt by dt plus dq by dz is equals to 0. This equation is equation 4. So this equation is nothing but, this is the continuity equation which is there in 1D and 1D unsteady unsaturated flow. This is the continuity equation. Now we'll apply momentum equation, right? So what does momentum equation will give us? So momentum equation, so we need to apply first what is known as Darcy's law. So what does Darcy's law give us? Darcy's law gives us Darcy's flux, which is a product of constant. This constant is known as permeability, multiply by SF. Here SF is nothing but how much amount of water is lost per unit head, per unit length of medium, which is equals to head lost per unit length, right? But if you look at this, this is nothing but head loss. And in the previous class we have learned about what is the total head. So the total head is equals to summation of psi plus z, which stands for suction head, and z stands for datum head, right? So we can modify this equation that for q will become k into, instead of h we'll write psi plus z per unit length, right? And this length could be in terms of z. This equation is equation 5. Let us say this equation is 5. Now we'll focus only into in equation 5. We can say that q is equals to k. I'm multiplying k inside, right? And this will be rate of change of k d psi by d theta into d theta by dz. We have applied partial differentiation here in k of dz by dz, right? So if you look at this equation, dz by dz is 1, so this will become k. We can take a constant out now. Or we can simply rewrite this equation like this term is known as soil water diffusivity. So instead of k, this term we can write it as d. So d will be d theta by dz plus k. So the final equation is 5k. Now this equation we can go ahead and substitute in this value, like this equation 6, we can go and substitute in equation 4. The equation 4 was d theta by dz plus dq by dz is equals to 0. So here instead of q we can substitute this value, and that will give us the final equation, which is known as Richards equation. So d theta by dt is equals to or plus d by dz, and instead of q we can substitute this value. This is nothing but a Richards equation. So this is all about 1D unsteady unsaturated flow. Now what we are going to discuss is about infiltration. Like what is infiltration, how does it occur, and what are the factors influencing infiltration. So if you look at the definition here, the definition of infiltration is very simple. It is the process of water penetrating from the ground surface into the soil, right? And there are various factors that are affecting this process. So we have enlisted like three factors here. The first factor is nothing but type of soil. So let us say there are two types of soil here. First we have a type of soil which is very dry, and one type of soil which is very wet. So we have two types of soil, one is dry, one is wet, and we need to see like what each type of soil will has a impact on or factors or how it will affect the infiltration process, right? So if you look at dry soil, so here in dry soil we know that the moisture content will be very less, right? So the volume of soil will be filled only with volume of solids, right? There would be any voids in there. So there are obviously more space inside dry soil, so it can absorb more water. So we can say that when the soil is dry, there is more void space, and water can fill those void space, right? So we can say that whenever the soil is dry, the infiltration will be more. But in case of wet soil means there is already the void is filled with water, some amount of water. Let us say it is 60% filled with water. So in that case, there is only 40% space inside the void to be filled by water. So in that case, we can say that if the soil is dry, the infiltration will be less. So this is the first factor which is affecting infiltration. The second factor was property of soil. Right? So depending upon the property of soil also the infiltration will be affected. So let us say if the property of soil is porosity. So if porosity is more, the infiltration will be. You need to recall the definition of porosity here. Porosity is what? Volume of void. So if the volume of void, there is more space inside the soil. So we can say that when porosity is less, then infiltration will also be less. And the vice versa is the opposite case. The third factor is very important, that is LULC, right? LULC, it means about whether the surface is filled with urbanization or it is filled with vegetation, right? So let us say there are two types of cover here. First is vegetated cover, that is the land is filled with vegetation, and other is urbanization. Let us see what happens in both the case. So in the first case, that is vegetation cover, right? And vegetation cover means the exposure of ground surface is with soil. So if it is a soil surface, obviously the infiltration will be more. But urbanization means the surface is not a ground surface, it would be a concrete surface. So in that case, the infiltration will be obviously less. So these are the factors that are affecting the infiltration process. It depends on the type of soil, whether the soil is dry or wet, or whether the soil is having porosity more or less, or then also it depends upon the LULC cover, like the land use cover. So these are the factors that are affecting infiltration process. So we know the definition of infiltration and we know the factors that are affecting infiltration process. Now let us derive, or let us see how different in how different ways we can define infiltration or represent infiltration. So we can represent infiltration in three ways. The first is infiltration rate. So infiltration rate, it means by what does infiltration rate means here? So infiltration means the rate at which the water is infiltrating. It means the amount of water or depth of water which is penetrating inside the ground surface over a period of time. So if you look at into the unit also, the unit is centimeter per hour. So infiltration rate gives us how much amount of water is penetrated over an hour. What does cumulative infiltration means? So cumulative infiltration will give us the accumulated amount of water that is going to infiltrate during the infiltration process, right? Since the beginning, like let us say we are noting down the time at which the infiltration process is going to start. In the first period, let us say there is infiltration of 10 centimeter. In the second period, the infiltration is 5 centimeter, and we want to get the cumulative infiltration for 5 hours. So what we are going to do, we are just going to sum the infiltration that has happened over the previous 5 hours, and we'll get the value. So that is nothing but cumulative infiltrations. The unit of it is centimeter. And the last is infiltration capacity. So infiltration capacity, what does infiltration capacity means? It is the maximum rate at which the soil can absorb water. So this is two different things. This is the rate at which the water is infiltrating, and this is the maximum rate at which the soil can absorb water, right? So these are the three ways we can represent infiltration: infiltration rate, cumulative infiltration, and infiltration capacity. Now there is some certain relationship between infiltration rate and cumulative infiltration. So let us see the relationship between cumulative infiltration rate and cumulative infiltration. So if we have infiltration rate with us, that is f of t, small f of t, and we want to get the cumulative infiltration, that is capital F of t, what we can do is we can just simply take the integration and we can get the value of f of t. So f of t is nothing but the integration of infiltration rate over a period of time, and the vice versa is the case for cumulative infiltration. Let us say if we have cumulative infiltration with us and we want to get the infiltration rate, what we are going to do, we are going to take the derivative of cumulative infiltration with respect to time, will give us the infiltration rate. Now there are two different types of infiltration. This is the same like it was there in evapotranspiration also, right? Potential evapotranspiration and actual. So this is the same thing. Here the potential infiltration means the maximum amount of infiltration that can occur, right? This is the maximum that can occur, and actual means what is actually has happened at the site. So that is denoted by FA and this is denoted by FP. Now there are certain ways when we can compare infiltration rate with rainfall intensity. So there are two conditions. So the first condition, what does it say? Let us say there is a condition where the rainfall is occurring at a rate which is higher than what the soil can absorb, right? So what will happen in that case? So this is the case at which there will be a ponding of water over the ground surface. Let us say the infiltration capacity of soil is 10 centimeter per hour. It can only absorb 10 centimeter of water per hour, but the rainfall intensity which is occurring at that time is 15 centimeter per hour, right? So the rainfall intensity is more than the infiltration capacity of soil. So over that period, what will happen? The excessive amount of water will be stored above the ground surface, and that is called as ponding of water. So this is the first case which they are saying is rainfall is occurring at a rate which is higher than the soil can absorb. Then the infiltration will be at maximum rate, right? This is the first case. The second case, what they are saying is if the rainfall is flowing at a rate which is lesser than the maximum, which the soil can absorb, then the actual infiltration will be equal to the rate of evapotranspiration. So from these two equations we can get the value of actual and potential evapotranspiration. When intensity of rainfall is more, we can say that actual will be equal to potential, but if the rainfall intensity is less, we can say that the actual rainfall infiltration capacity would be equal to the intensity of rainfall. So these two cases are really important. Now let us see like what are the different methods to measure infiltration. So unlike like before also, when we talked about rainfall, there were instrument called as recording non-recording rain gauges, right? When we studied about evaporation, then we studied about instrument called as evaporation pan. Then we talked about evapotranspiration, there we studied about an instrument called as lysimeter. In the same way, when we want to record or measure infiltration, the instrument which is most commonly used is called as ring infiltrometer. So there are two types of instruments, single ring and double ring. The process to record or measure the infiltration in both the instrument are same. The only thing is that the double ring takes into account of two different sets of ring, whereas in single ring there is only one instrument. We'll see both of them one by one. So the first instrument is single ring infiltrometer. So what we usually do is, the overall depth of this instrument is 50 centimeters. So what we do, we immerse the instrument 30 centimeter into the soil and we expose the about 20 centimeter above the atmosphere, right? And what is done is, water is filled in the ring up to 5 to 10 centimeter of depth. So if you can see here, the only 5 centimeter of water is filled here above the ground surface. And what we are going to do, we are going to record the time for which the water will get infiltrated into the surface, and that will give us the infiltration rate. But there is only single ring here, but when we look into this instrument, there are two rings, right? The first ring here is inside, which is of 30 centimeter, and there is an outer ring which is there for 60 centimeter. Like, why we are using this outer ring? Because we want to prevent the lateral spread of water from the inner ring. Obviously there will be some spread from the inner ring to the outside of soil. So in that is what we want to prevent here. So in order to do that, we are providing it with another outer ring also. And the other process is all same, just they are reducing the depth here. The outer ring instrument is dipped inside only 50 centimeter, and other process is same. You just need to record the time here for how much time the water is getting infiltrated. That is what is needed here. So there is one example also based on infiltration rate and plot. This is a really good example to understand how we are getting the data from the experiment of single ring and double ring. So let us say we have recorded the time and we have recorded the cumulative depth. So in the first minute, the cumulative depth that was infiltrated into the ground was 1.2 centimeter. In the second minute, the cumulative depth is 2.9. It means 0.9 meter was the actual depth, but since we are calculating cumulative depth, so they have added and given us the value of 2.1. So this instrument, this all data set is we are getting from single ring or double ring infiltrometer. We are recording the time and we are recording the depth of water that is getting infiltrated. Now what they have asked us here is, they are asking us to calculate infiltration rate. So by the definition of infiltration rate, we know that infiltration rate is nothing but amount of water that is getting infiltrated per unit time. So all we need to do is we need to divide cumulative depth with the time. We'll get infiltration rate, and then we need to plot the infiltration curves. But let us look at the unit here. Here the unit for time is meter, so we need to convert meter into R, and also the depth given is cumulative depth. So we need to calculate the actual depth of water that was infiltrating during that particular hour or particular minute. So let us see the procedure here. So if you look at the first two columns are the given data set. Now in the third column, what we are doing here is we are just converting meter to R. So this is a simple conversion, right? We have divided it by 60. The next thing is to calculate incremental time. Incremental time means incremental R. So we are just subtracting the first value with the other value, like how much values have been incremented here. So we are subtracting the last value with the first value, last value with the first value, and we are getting the incremental value, right? The next is to calculate incremental depth. So how you are going to do that? Again, you are going to subtract this value with the previous value. So 2.1 minus 1.2 gives us 0.9. then 3.8 minus 1 2.1, it gives us 1.9. So now we have incremental time, you have incremental depth. If you divide these two terms, that is incremental depth with respect to incremental time, it will give us infiltration rate. So they have divided 1.2 with 0.02 and they got the answer as 72 centimeter per hour. So this is what we are going to plot, infiltration rate. This is the plot. So if you look at the plot here, they have plotted infiltration rate. So the red curve is nothing but the infiltration rate. So if you look at the infiltration rate, what you can say is that initially the infiltration rate was very high for the first minute, right? And at a certain point, after a certain point of time, let us say after 14 hours, what happens is the infiltration rate becomes constant. And why is that? Once the soil is completely filled with the volume of water, after that the infiltration rate will become constant. So initially the water may be filled with less volume of water. So at that time it can intake more water. So the infiltration rate is more, that is 72. And over the period of time it becomes constant, right? So this is what infiltration rate looks like for any soil profile. The next is cumulative infiltration. What does cumulative infiltration? This is nothing but the average data set, like whatever data set was given to you, this second column, they have just plotted this. So the main answer that they have asked was to plot infiltration rate. So the red curve is the required here. Now there are different other empirical equations also which can be used to estimate infiltration. So there are different sets of equations. So first we'll look into only empirical equations. So empirical equations are of like there are three empirical equations or two empirical equations. First is kostiakov equation, Horton's equation, Horton equation. So here we'll be discussing about these two equations, in mostly kostiakov's and Horton's. Then there is another equation called as Green-Ampt equation and Philip equation. These are theoretical equations, so we need to derive those equations. Now let us see the first equation, which is kostiakov's equation. So the kostiakov equations will give us both the thing. It will give us also the infiltration rate. So infiltration rate is given by this equation. Ft is equals to k of k t raised to the power of minus alpha. And if we take the integral of this, we'll get the cumulative infiltration. So f of capital F of t is nothing but the cumulative infiltration. And we got this equation by simply taking the integration of f of small f of t. So whenever we use any of the empirical equation, what we are going to do this, the empirical equations are very like it is very difficult to remember them. So what we can do is we can simplify them and we can convert this equation into a form of linear equation. And how we can do that? We can just simply do that by taking natural log on both the sides of equation, which will give us a simplified equation in a which is nothing but a linear equation. So let us see that how they are doing that. So if you look at this equation, they have taken natural log on both the sides, right? So if you look at this equation is nothing but it represents y is equals to mx plus c, right? So the first term is c, that is natural log of k divided by 1 minus alpha. This term represents c, it gives us the y-intercept. And the next term is nothing but mx, right, because it's product of m with respect to time. So the first term is nothing but slope, so 1 minus alpha represents slope. So whenever we are solving any of the empirical equations, the first thing to do them is to just simplify those equations. So remember the equation and just simplify them by taking natural log on both the side and converting into a straight line equation, because that is what we are going to plot. Similarly, if you look at Horton's equation, so how does this is the Horton's equation. If you want to calculate infiltration rate at any given time, all you need to do is you need to have two values. The first value is the initial value at the time of infiltration begin, that is called as F0. So if you know the infiltration value at the very beginning and you know the value that becomes constant after a certain period of time, that is what we are seeing here, right? See, this is the value, infiltration value, which was there at the beginning. This is FO, and the volume of water that becomes constant. So after a period of time, the value of infiltration rate becomes constant. So if you can see that the value of 10 point something around 10 is nothing but the constant value. So we can say that that constant value is FC. So if we know FO, if you know FC, we can calculate infiltration rate at any given time. So similarly, like how we have converted Kostiakov's equation into a straight line equation, same thing could be done with respect to Horton's equation as well. So if you look at this equation, what they are doing is that taking natural log on both sides, and they are converting the TDS equation into a simplified form. So if you look at here, this is nothing but y is equals to mx plus c form, right? So this natural log of f0 minus fc is nothing but the c intercept value, and k is nothing but your slope. So if you plot these points, you'll get a straight line equation, and from that straight line equation you can calculate your y-intercept. That y-intercept is nothing but your natural log of f0 minus fc, and the slope of this equation will give you the value of k. So now that you know the value of k, you know that the value of f0 minus fc, you can calculate infiltration at any given time. Now let us say some numerical example based on both the equation, that is Kostiakov's equation as well as Horton's equation. So if you look at here at Kostiakov's equation, this is the given data set. They will give you the time, they will give you the cumulative depth. But what they have asked here is, they have asked us to estimate the parameters of Kostiakov's equation. So the parameter of Kostiakov's equation is A and B, right? If you look at the equation of Kostiakov's, this is the parameter. So we need to calculate A, we need to calculate B. What they have given is here is, they have given us T and they have given us cumulative infiltration, right? Yeah. So what we are going to do is simply we have taken the given data, we have converted minutes into hours, we have calculated incremental time, we have calculated incremental depth, and we have calculated infiltration rate. So the process is quite similar which was done in the previous example also. But if you look at this equation here, we need to take a natural log. So we have taken natural log on both sides because we want to get a simplified equation. This is the final equation when we compare with the straight line equation. So this is nothing but y, this is nothing but m, this is nothing but a. So if we get the value of intercept a, that is, this is the value of intercept, right? 3.315. So this 3.315 is nothing but the value of natural log of a. And we also got the value of slope, that is 0.699. So that 0.699 means 0.7. This is nothing but the value of b. So we got the value of b directly as 0.7. But in order to get the value of a, which is 3.315, is the value of natural log of a. So we need to take the anti-log of this. So anti-log of 3.315 will give us the value of a. So here if you can see that they have taken anti-log of a and they got the value as 27.52. So now that we got the value of a, we got the value of b, we can calculate f of t. Right, so we have got the cumulative infiltration, but at the same time if we want to calculate infiltration rate also, so we need to work on this equation, above equation. So in the above equation we need to calculate value of alpha and we need to value of k of k. So both of this term depends upon a and b. So if you look at this equation, alpha is nothing but 1 minus b and k of k is nothing but product of a into 1 minus alpha. So since now we know the value of a and alpha, we can calculate k of k, we can calculate alpha also, and we can get the value of f of t also, that is cumulative infiltration, and we can get the value of infiltration rate as well. Right, so these are like very simple example. In the same case for Horton's equation also. So whenever we are working on Horton's equation, there are two things that are very important. The first thing is, what is the value of initial infiltration, that is f0, that is at the beginning of infiltration, and what is the value of fc, that is constant infiltration. So if you look at the later stage, the constant value is 1. So f of c is 1 and f of 0 is 0, right? And that's the initial value. So if you look at this thing, the time, the initial value was 0. So infiltration capacity they have given to us, f of p. So we need to calculate f of p minus f of c. So how we are going to do that? We need to calculate f of c. So f of c, from the table itself we know f of c is nothing but 1. So we are going to simply minus 5.6 minus 1, it gives us the value of 4.6. And we are taking natural log of this because we are going to plot natural log versus time, so that the equation becomes straight line, and then from the straight line equation we can compare Horton's equation and we can get the value of f of 0 minus f of c, and we can get the value of k, right? So if we look at this equation, if we see at the value of y-intercept, that y-intercept value is nothing but the natural log of f0 minus fc. So we need to take the anti-log, so we got the value of f0 minus fc. And similarly we want to calculate the value of k. K is nothing but slope. So here the value of k is minus 3.15, which is done here. So now that we got the value of K, we got the value of F0 minus Fc, we are just simply going to substitute into the standard equation of given by Horton's. So this is the standard equation. We got the value of Fc, right? F0 minus Fc was 10.49. We know the constant value is 1. So we added it to 10 point. So we got the value of F0 minus Fc, that is 11.49 minus 1. So it gives us 10.49. And e to the power of k. So the value of k is 3.1 here. So minus 3.1 times of t. So this is the final value of Horton's equation that is derived from this equation. So these are like two very simple approach to calculate infiltration rate as well as cumulative infiltration for any type. It depends on the data set that is known to us. If you know the value of constant value of infiltration, we can go for Horton's equation, or else we can use Kostakov's equation. So these are the empirical equations. So there are other equations that are known as theoretical equations. So let us see those equations. So there are two theoretical equations. First is Phillips equation and another is Green-Ampt equation, right? So let us see first Phillips equation. So if you look at the Phillips equation, this is the equation given by Phillips to calculate cumulative infiltration. So here the cumulative infiltration, the equation is given by St to the power half plus Kt. So here there are two terms that are taken into consideration to give cumulative infiltration. First is S. So S is nothing but it is known as sorptivity. And what the sorptivity means, it takes into account the suction force, that is the suction head, which we have studied before, which is known as psi, which is given by psi. And the other term is hydraulic conductivity K, like how much amount of conductivity is there in the soil. So it takes into account those two things and it gives us the infiltration rate. Now again, this is cumulative infiltration. If we want to calculate infiltration rate based on Phillips equation, what we need to do is we need to take derivative of this equation to get the infiltration rate. So here we have taken the derivative to calculate the infiltration rate equation. So this is the infiltration rate equation. F of t is equals to 0.5 St to the power of minus half plus K. So if you look at any example given by this thing, again what we need to do is the infiltration rate is something like this. If we want to compare it with a straight line, it will be very easy to calculate. So what they are given us is, here is the soil column has a saturated hydraulic conductivity of 10 mm per hour. So they have given us K value and also they have given us S value, and they are asking is using the Phillips equation generate the infiltration curve. So simply what we are going to do, we are directly going to use this equation, infiltration rate equation, 0.5 S to the power of minus 2 plus K, because we know the value of Sn, T and time is changing, right? So here first we have plotted time, 1 minute, 2 minutes, we have converted into hours. We know the cumulative infiltration force F, we know infiltration rate calculated, that is these two terms we have calculated using these two formulas, just by keeping S and K constant and varying the time in R. So we got the value of cumulative infiltration, we got the value of infiltration rate. So we can now plot both the things. Infiltration rate is the red curve and cumulative infiltration is the green curve. So you just have to substitute S and K in this equation. In both the equation you will get cumulative infiltration and infiltration rate. This is another example given by Phillips equation. Here they have mentioned time and cumulative infiltration, right? And what they have asked us is determine the parameter. Now this is completely opposite of this. Here they have given the parameter and they have asked us to derive the infiltration rate and cumulative infiltration. In this equation they have done completely opposite. They are asking us to get the value of parameters. So whenever we are supposed to calculate the parameters, what we are going to do, we are going to convert this equations of this curve of infiltration, which is like an exponential equation, we are going to convert this equation into a straight line, and then by comparing the standard equation we can get the parameters, right? So see here also, this is the standard equation of infiltration rate. We are going to convert this equation in terms of a straight line by simply taking natural log on both sides, right? We can do that. So let us see the procedure. The procedure is same that we have done before. Time is given to us, but it is given in minute. We need to convert it into R. Cumulative infiltration is given. We need to get incremental time and incremental depth. Then by dividing incremental depth with time will give us the infiltration rate value. The last term here we have taken is square root of T just to take into account this term. So we have taken square root of t here. And in the end, what we are going to do is we are just going to plot infiltration rate versus time, but we are not going to plot it versus time. We are going to plot it versus this thing. So we are going to plot these two terms, last two columns. In all the previous terms, whenever in previous equation, the thing was the time had no power with it, associated with it. But when we talk into Phillips equation, the time has a power of -2. So we need to plot versus t to the power of 2. So we have taken square root of t, and then we are going to plot last two columns here. That is what we have done here. Now the equation is straight line. So the first term will give us the value of, like, that is the slope. Slope will give the value of k, that is coefficient of sorptivity and in order like hydraulic conductivity, and the y-intercept will give us the value of sorptivity values. So this value and this value we have compared with standard equation, and we got the value of sorptivity and hydraulic conductivity. Now the last thing that is left here is to take into account or to derive Grimm-Knapp equation. So this is one of the important equation, and this is what we are going to continue in the next week also, when we talk about of detail of ponding and how does the ponding time, what is the equation of ponding time. So in that equation also Grimm-Knapp equation takes a very important role. So if you look at the equation here, final equation that is derived here from Grimm-Knapp equation, it will equal to the final equation here. So these two are the equations that we need to remember. These are the Grimm-Knapp equation, right? So the first equation, that is capital F of t, this is equation for cumulative infiltration. So if you look at this equation, what are the terms here? So the first term is F of t, which is cumulative infiltration. Second term is psi, which is nothing but suction head, right? Theta is nothing but moisture content which is there in the soil, and K is hydraulic conductivity. So if we know these four parameters, we can calculate F of t. And also the another equation is used for infiltration rate. So for infiltration rate also similarly we need four values, that is coefficient of hydraulic conductivity, we need section head, we need moisture content, and also at the same time if we know the cumulative infiltration value, we can calculate infiltration rate. Let us see if there is some example based on this. So there are no given example in this. I think we need to take few example based on Grimm-Knapp equation as well. So we'll solve few example now, like all the theory that was there in subsurface flow we have covered here. So we started with subsurface water, like how does the water, the rainfall which is occurring is getting divided when it comes onto the surface. It divided into the intercept and storage, then some of the water it flows onto the ground surface and becomes surface runoff, and the remaining of the water gets infiltrated, and there is what infiltration is. So we talked about infiltration, then we talked about different zones of water that is there inside the ground surface, that is unsaturated zone and saturated zone, and how does the water flows in the unsaturated zone, and and what it is called, that is it is interflow, and the water which is flowing in the saturated zone is base flow. Then we also looked into the soil profile, where we got to know about two different definitions, that is porosity, and we also learn about what is water content or moisture content. Then based on those two definitions, we got to know like what could be the range of moisture content. So it could be 0 for dry soil, and when the soil is completely saturated, it could be equal to porosity. So the range for moisture content is 0 to porosity, right? Then we looked into the Richards equation. We looked into the derivation of 1D and steady and saturated flow equation, which is known as Richards equation. So what we did here is we have simply used RTT theorems, and we have applied for continuity and momentum equation, and together by combining those two derivation of those two equations using RTT, we got to know the Richards equation, right? So we have derived this equation. So this is the equation that we get when we apply RTT to the continuity equation, right? dq by dz plus d theta by dt. Now what we need to do is we are going to calculate the value of q, that is Darcy's flux, by applying RTT to the momentum equation, right? And we'll get the value of q and going to substitute here in this equation 4. So when we apply momentum equation, we'll get the value of q. So this is the value of q that we get when we apply momentum equation, and this value we are going to substitute in the above equation, and this will give us the final equation. So this is the final equation of 1D unsaturated, unsteady unsaturated flow. This equation is known as Richards equation. So this is very important equation. Next thing that we studied was we studied the definition of infiltration, and we looked into the what are the different factors that are affecting infiltration, right? So we know the definition by now, that it is the process of water penetrating into the ground surface, from the ground surface into the soil. Then there are three different factors that are affecting infiltration. First was type of soil, where we got to know when the dry soil is there will be more volume of void available for the water to fill those voids, so obviously the infiltration will be more. Then we looked into soil moisture. If the soil moisture is higher, the infiltration will be less. Then we looked into land use, land cover, where we looked into like if the cover is vegetated or urban. Obviously for urban the infiltration will be less because of the surface condition. It will be having a concrete surface, but when we talked about vegetated surface, it will be exposed to soil surface, so obviously there will the infiltration will be more in that kind of surfaces. Now this is the profile, soil moisture profile, like how does the value of moisture content varies with respect to depth, right? So initially the soil is dry, like at the beginning of the stage the soil is dry, so at that time we can say that the moisture content will be 0, right? So theta would be 0 initially. Then what happens is during the rainfall event, as the water move down, it wets the soil. So initially as the depth is increasing, the moisture content is also increasing, right? So we have to look in both the direction. We have to look with respect to depth also, and with respect to how the soil moisture content is varying. So let us look at this point. So at this point theta is 0, depth is 0, and there is no rainfall. Now as soon as the rainfall begins, what happens is water will start infiltrating below. So the depth of water infiltrating will goes on increasing, and with the same time the moisture content will also increase in the x direction. So there will be variation in x direction, which will be in terms of moisture content, and there will be variation in terms of y direction, which is nothing but the water that is infiltrating inside the soil. So near the surface or just below the ground will be approaching saturation, right? So what they are saying is that is theta and porosity would be at the ground surface as just below it. This is called as saturated zone. So saturated zone is the zone where entire soil void is filled with water. So what happens at that condition? We know that at that point of condition, moisture content will become equal to porosity. So look at this equation. At the saturated zone here, if you look at this part, here theta is equals to m, because in the saturated zone what happens is the volume of void is completely filled with volume of water. So here we'll get the moisture content will become maximum, and just after the saturated zone or saturation zone there will come a termination zone or transmission zone. What happens in transmission zone is the moisture content is again decreasing with respect to depth. So if you look at this figure here, the moisture content was maximum, again it is dropping, and this is known as transmission zone. And after a period of time, after transmission zone, there will be another zone, wetting zone, where there will be a sudden drop, like there will be a fast drop in the moisture content. So that is called as wetting front. So that wetting front is nothing but it is a sharp discontinuity between the wet soil and the dry soil. So here again that the moisture content will decreases, and here we can see that from the plot it is decreasing rapidly. So this is nothing but a soil moisture profile. So how initially the moisture content was 0 before the rainfall, and just after the rainfall peaking in the saturated zone, the moisture content become maximum. And once it becomes maximum and again it start penetrating, what happens is the moisture content is going to decrease, and ultimately it falls below. And this curve is nothing but wetting front. This is the region where the moisture content reduces rapidly. Then we studied about representation of infiltration, right? We know there are three different types. First is infiltration rate. Infiltration means the amount of water which is infiltrating per unit time. So if if we can remember the unit, it will give us the idea what is infiltration rate. And also remember the notation. The notation for infiltration rate is small ft. Whenever we talk about cumulative infiltration is the cumulative depth of water that is penetrating inside the soil, which is represented by f of capital T. Then there is something called as infiltration capacity, which is nothing but it is the maximum rate at which the soil can absorb water. So this is the actual rate, this is the maximum rate. Then we studied about the relationship between infiltration rate and cumulative infiltration. So simply to summarize this, if we have infiltration rate with us, we can calculate cumulative infiltration just by taking integration of that, right? And the vice versa is the case to calculate infiltration rate if we have cumulative infiltration. Then we talked about two different cases, like to know understand two parameters, that is actual infiltration. Let us say we want to calculate actual infiltration rate f of a. So how we can do that? So there are two cases. The first case is when the rainfall which is occurring is less than the infiltration rate, which is if I is higher than, if I is higher than the maximum potential infiltration. So what happens during that case is f of a will become equals to fp. But there is another case also. What happens sometimes is the rainfall infiltration rate would be less than the potential infiltration. So during that case, the actual potential will become equal to rainfall intensity. So just remember, just to summarize this, if we want to calculate actual infiltration rate, we just need to compare infiltration rate with the rainfall intensity. If rainfall intensity is less, we can say that potential actual infiltration will become equal to intensity. If potential infiltration is less, we can say that actual infiltration will become equals to potential infiltration. So this is just to calculate actual infiltration rate. Then we talked about measurement. So whenever we talk about measurement of any hydrological variable, there are different ways. So obviously there are some instruments that could be used to measure infiltration, right? In accordance, like in the previous class, there were also instrument based measurement. So here for infiltration, there is one instrument called as ring infiltrometer. So there are two types of infiltrometer that we have discussed. First was a single ring and another was double ring. The process is, the methodology is same. We just need to measure the time and amount of water that is infiltrating from a certain level to a certain level. But the only thing is that in single ring consists of only one ring. In the double ring there are two different setup. Like one is called as inner ring and another is called as outer ring. But if you use double ring infiltrometer, it will give a good idea about infiltration, as it prevents the lateral spread of water from our soil, right? So it will give a more accurate result in comparison to single ring infiltrometer. Then we looked into some graphical representation of infiltration curve as well, right? So we know we need to plot infiltration rate. So infiltration rate by definition is nothing but depth with respect to time. So here we have given cumulative depth and the time is given in meters. So obviously the conversion is needed. Time is converted into r, depth is converted into incremental time and incremental depth. Then just by dividing incremental depth and time, we got the infiltration rate here. So the red curve is infiltration rate and green curve is nothing but the cumulative depth that was given to us. Then we studied about infiltration measurement or estimation of infiltration using empirical equations. So we talked in detail about two equations, that is Kostiakov's equation and Horton's equation. So whenever we talk about infiltration equation, empirical equation, we just need to remember the equations. So the first equation was Kostiakov's equation. So Kostiakov's are given equation for infiltration rate, that is Ft. That is K of K t to the power of minus a. So here K of K and minus alpha are nothing but they are empirical constants that is given by Kostiakov. And if we take the derivative of this equation, we'll get the value of, integration of this equation, we'll get the value of cumulative infiltration f of t, right? So we just need to calculate the constant values. If we know the constant values given by given by Kostiakov, we can calculate infiltration rate for any given time. But if we can see the equation of given by Kostiakov's equation for cumulative infiltration is quite tedious. So we just want to simplify this equation for a graphical representation. So what we are going to do is we are going to convert this equation into an equation of straight line, and by then we'll plot a straight line and we'll get the value of slope and intercept, and those slope and intercepts are nothing but the constants of cumulative infiltration given by Kostiakov, right? Similarly for Horton's equation also, so Horton proposed an exponential relationship for infiltration rate observed under ponding condition. So what is ponding condition? So in the previous case when we talked about when the intensity of rainfall is more than the infiltration potential, right? So what happens at that duration? The amount of rainfall that is coming is more than the capacity of water to absorb it. So in that condition ponding will occur. So that is nothing but ponding condition. I think this will be covering next week in a more depth, like what is ponding and what is the time of ponding and everything. So if we look at into the equation here now, so in this equation there are two parameters that are need to be known to us. The first thing is what is the infiltration rate at the very beginning, that is FO, and the second term is FC, which is constant value. So over a period of time we know the value of infiltration will become constant, right? And why is that it's becoming constant? Because the entire volume of soil would be completely filled with, the voids of soil will be completely filled with water. At that time the infiltration will become constant. So here also similarly, how we did for Kostiakov's equation, we need to change this equation into an equation of straight line so that it would be easy for us to get the value of constant. So the constant here is nothing but k, right? So we need to get the value of k, and also we need to get the value of initial value of infiltration, because we don't know the value which is there, like what is the infiltration rate at the very beginning. So in order to get this value, we are using Horton's equation and we are converting the equation into a form of straight line. So if you look at this, we have converted this into a form of straight line. So here the y-intercept will give us the value of f of o minus f of c. Since we know the value of constant, we can get the value and subtract f of c, will get the value of fo. That is the initial infiltration rate at the very beginning of infiltration. And the next term is k. So k is nothing but the slope. So if we know the value of straight line ka slope, we can get the value of k, and based on that we can calculate f of t. Then we looked into theoretical approaches. So there are two theoretical approaches. First is Phillips equation and another is Green-Ampt equation. So Phillips takes into account two different parameters. First is sorptivity and next is hydraulic conductivity. So sorptivity is nothing but the suction head, which we talked about at the very beginning of the class, and hydraulic conductivity is nothing but k. It depends upon, it is the intrinsic property of soil. So here Phillips has given the equation based on equation for cumulative infiltration based on S and K. And if you take this derivative of this equation, you will get the infiltration rate equation, which is f of t is equals to 0.5 st minus half plus k. Now if we compare this equation with straight line equation, we will get the value of y is equals to mx plus c. So if we know the intercept, it will give us the value of k, and if we know the value of slope, it will give us the value of 0.5 s or s. But the one thing we need to remember is whenever we are plotting Phillips equation, we need to plot infiltration rate with respect to t to the power of minus half. We need to plot it to the power of minus half here. So if you look into the example also, here we are plotting it with respect to time to the power half, right? In order to get the parameter that is S and K. Then we looked into another equation, that is Green-Ampt equation. Green-Ampt equation is very important. It gives us a cumulative infiltration as well as infiltration rate. So all you need to remember is the final equation that has been derived using Green-Ampt. So this is the equation. So this equation is needed. So this equation is nothing but when we are going to derive the time ponding equation in the future classes, at that time also we are going to take this equation as a reference equation for infiltration rate. So we are going to take this equation as a reference and we are going to derive ponding time. So this is the theoretical part that we have covered so far. Now what we are going to do is we are going to look into few numericals example as well. So if you want, you can solve this example. The observation attained for the infiltrometer experiments are given. The diameter of the infiltrometer infiltrometer ring is 20 centimeter, determine the constant infiltration rate. So we need to determine the constant infiltration rate, which is FC. So they have given us time, they have given us cumulative volume of water also. So we can solve this equation. If it's a numerical we want, we'll just adjust few of the things here. So let us say we have time in minutes, and those time is nothing but 0, 10, 20, 30, 60, 90 and 120. This is the time that we have in minutes. And at the same time we have cumulative volume of water added in centimeter per cube. So this is cumulative, and at the same time it is volume of water, which is given in unit of centimeter cube. So let us see the values. So the values are 0, 100, 300, 450, 750, 800, 1200. So these are the values that are given to us. Now let us proceed, and we need to calculate here is constant value. So what is the constant value of infiltration rate? So let us name it as FC. So we need to calculate constant infiltration rate, which would obviously would be in centimeter per hour. So the first thing we need to calculate is we need to convert this centimeter cube of volume of water into centimeter. And how we can do that? They have given us the diameter of infiltrometer, right? So let us say the diameter of infiltrometer ring is 20 centimeter. So what we can do is we can calculate the area from diameter, and we can divide this cumulative volume of water, and we can get the cumulative depth of infiltration, right? So what we are going to do is, first we are going to convert time from minutes to hour. Then we are going to calculate cumulative depth simply by dividing cumulative volume of water with respect to area. Cumulative volume with respect to area. Then we'll calculate incremental cumulative, right? What is the increment in depth and incremental in time? Then we are going to calculate incremental depth and incremental time, and later by dividing these two terms we'll get the value of infiltration. So let us first convert this time from minute to hour. So the first value is 0, second is by dividing 10 by 60, then 20 by 60, 30 by 60, 60 by 60, 90 by 60, and so on for 20 by 60. Then we'll get the value of area. We can calculate the value of area, and we can get cumulative depth, right? So the first value is obviously 0, because cumulative volume of water was 0. Second is cumulative volume of water is 100. So let us divide it by area. So area is pi by 4 of 20 square. So this will give us the value of cumulative depth. So this value is 0.318, and similarly we can calculate other value also. So 300 divided by pi by 4 into 20 square. This is 0.955, 1.433, 2.388, 2.54. The last value is 3.82. So now that we know the value of cumulative depth, we can get the value of incremental depth also. So all we need to do is we need to subtract it with the prior value or the next value. So you can calculate incremental depth and incremental time now. First value will be 0.38 only. The next value is we are going to subtract 0.955 minus 0.318. So this is 0.637. Last value is 1.28. So now that we have incremental depth, we can also calculate incremental time. First value will be 0.16. Next value will be 0.167. This will also be 167. Then it would be 0.5, 0.5 and 0.5. Now we have incremental depth with us, we have incremental time. The next thing is to calculate incremental, or we need to calculate infiltration rate by simply dividing incremental depth with respect to incremental time. We will calculate infiltration rate now. So we are going to divide 0.318 divided by 0.16. So we will get the value of infiltration rate. It is coming to be 1.98. Then the next term. Next term is 3.184. So in the similar manner you can calculate the infiltration rate for all the incremental depth, and later you will see this is the second term. The next term is 0.478 divided by 0.167, that is 2.862. Next term is 0.955 divided by 0.5, which is 1.91. 0.152 divided by 0.5, which is 0.30, and last term is 1.28 divided by 0.5. So if we have more points, we can say there would be a point. If we have more data set, we can say that there would be a point where this number would keep on increasing, like repeating same. So in that way, we can say that 0.51 is the constant value. So for that, we need more data points. So if we can solve this example, which is given in the assignment. So if you can see, there are more data points here. So for the last 3 points, I'll say there will be a point where the infiltration rate will become almost constant. So that value where the value of infiltration rate is repeating, or it is remaining constant, is what they have asked us to calculate, constant infiltration rate. So you'll get that value. For the same question, they are also asking us is the average rate of infiltration for the initial 30 minutes is. So for the initial 30 minutes means only up to this point they are asking us to calculate the average rate of infiltration. So we need to take the average of the infiltration rate which we are getting and just divide it and take the average of that. So if we are able to solve the same example, that is question 11, we can solve example 12 also. The only thing is we need to solve it till initial 30 minutes, and last at the end we need to take the average of that. Then the last question is the data obtained from the infiltrometer test are listed in the table given below. Now they have changed the diameter of ring and the initial infiltration rate is. So they are asking us to calculate initial infiltration rate, that is FO value they are asking us. So FO value can be calculated, right? Let us see how we can solve this kind of example. So here they have given us time, which is 1, 5, 10, 15, 25, 30. I'm only taking up to 30. Further, the same process you can use till different time. 25 and 45. I'm only going to solve till 45. Later for 60, 75 and 110 you can continue. They have also given us infiltration rate, right? So what we can do, we can convert this time which is in minute, we can convert this into hour. We are converting into hour, we are getting 0.07, 0.083, 0.167, 0.133, 0.50 and 0.750. Then they have given us infiltration rate, that is small f of t they have given us. They have given us value of 21, 15, 11, 9, 6 and 4.2. So this value they have given us. Now what they are asking is, they are asking us to calculate the constant value. So what we can do is, we can subtract f minus fc here, right? So the value of f that they have given is here is 21, and we need to calculate the value of fc. So if you look at the given data set, we can say the value of 3.1 is repeating, or which is saying constant. So we can say that the value of fc for the given example is 3.1. So we can subtract 21 by 3.1 and we can get the value of f minus fc. So this value will be 17.9, this will be 11.9, 7.9, 5.9, 2.9 and so on. So we get the value of f minus fc. If we take the natural log of f minus fc and we plot the value with respect to time, we will get a curve, right? and using that curve we can get the value of f0 minus fc. So what we can do, we will calculate this value, natural log of this value. So natural log of 17.9, natural log of 11.9, natural log of 7.9. So we will calculate this value, and later what we are going to do, we are going to plot this. So we are going to plot time in R versus natural log of f0 minus fc, this column, last column, and we will get a equation something like this, which is a straight line equation, which would be my equals to mx plus c. And if we compare this equation, we know from this equation c is nothing but the value of k and m is nothing but the value of natural log of fo minus fc, right? So using this, we need to calculate the value of infiltration rate, right? That is ft. So what we are going to do, we are going to calculate natural log of f0 minus fc. We'll get some values, and they have asked us to calculate this value. So we'll get the value of, let us say we get the value of this as 100. Then we'll take antilog and we'll get the value of fo minus fc something, let us say x. We know the value of f of c is 3.1, so f of o would be nothing but x plus fc. So we'll get the value of f of o. So they have asked us to calculate the value of f of o, right? So that we can calculate now. So like this is the example that they have asked us in the assignment, and there are more equations or more questions that you can solve using some reference book. Like you can use Subramaniam, you can use Ventica if you want to solve few more examples. And also if you can look into the theoretical question now, like they have asked Phillips model relates to cumulative infiltration capacity as a function. So if you can recall the today's class, you simply know the answer by now. Like what are the terms that are there in Phillips model. Then infiltration measured using double ring infiltrometer is more accurate that of from single infiltrometer. So we know the reason now why we are using double ring infiltrometer and what are the limitations of single ring. Also, what are interception losses? At the very beginning of the class we studied about types of interception losses. Then we studied about two different cases. What will happen if the rainfall intensity exceeds the infiltration rate? The infiltration will become equal to. So we know there are two cases. If you recall those two cases, you will be able to answer question 6. Then they are asking the moisture content in which the zone is above filled capacity but below saturation. So they are saying moisture content in which zone is above filled capacity but below saturation. So you just need to recall the soil moisture profile. So there are 3 different zones, right? The first zone was saturation zone, then there was transmission zone, and then there was wetting zone. So we need, if we know that, then we can answer this question also. And dash is responsible for the flow of water in unsaturated medium. So you need to recall at the very beginning of the class what we studied about unsaturated medium. So we studied about total energy, right? So in the total energy, we know there are 3 different forms of energy. First is due to suction, then another is due to datum, and then there is kinetic energy. So then we know like why we are neglecting kinetic energy and all those things. So if you recall those things, you can answer this. Then they are asking which of the following equation is not used for infiltration capacity. So we know, like by just looking at the option also, we have studied now different empirical equations and theoretical equations. So if you remember those names, then the names of those scientists, you can easily answer this question also. Then they are asking the flow towards the stream from the saturated zone beneath the ground surface is termed as. So we have covered this also. We know like how below the ground surface the zones are divided into 2 parts, unsaturated and saturated, and what water is like, how the flow of water inside the unsaturated flow is termed as, and what is the term for flow of water beneath the saturated zone, right? So we know, if you recall those definition, you could be able to answer. And also lysimeter is used to measure. So this is from previous class. So you need to recall like lysimeter is used to measure which of the hydrological variable. So I think everything we have covered in this today's session. We have discussed the assignment questions, and also we have discussed numericals. The only thing that is left is for you guys to revise Grimdam-Tickwen derivation. So if you can recall like the recorded video lecture, you could be able to understand the Grimm-Temp equation derivation. Apart from this, we have covered everything. We have covered numericals based on Kostiakov. We have covered numerical based on Horton's. We have covered numerical based on Phillips equation. Then we have studied about how to calculate constant infiltration rate and also the cumulative infiltration, right? So in the next class, I think we can solve one numerical based on Grimm-Temp equation also. So that would be very useful for us. So I think we can take one example here in order to calculate infiltration for Grimm-Temp model. Like apart from for waiting for next class, instead of waiting for next class, we can solve a numerical now as well. So we'll take an example based on Grimm-Temp equation only. So let us say we have a Grimm-Temp model. We need to derive or determine its constant, that is A and B, right? And at the same time also we need to calculate infiltration rate, that is F of t, and cumulative infiltration. Cumulative infiltration is capital F of t. So they have given us both the things. They have given us time for t equals to 6 hours. They are saying when the time period is 6 hours. So they have provided us with given data set also. They are saying time in hours is given to us, that is 0, 0 0.5, 1, 2 and 4. They have given us small ft, that is infiltration rate, and capital Ft, that is cumulative infiltration. Values are 5, 3.6, 2.8, 1.7 and 1.3. And for cumulative infiltration, so we should write the units here, centimeter per hour and centimeter. For cumulative infiltration, the values are 0, 2.2, 3.7, 6, 9.1. So these are the values that they have given. Now first thing what we are going to do is we are going to write the equation of infiltration rate given by Grimm-Temp model. So that equation is small f is equals to function of k plus k psi delta theta upon capital F of t. So this is the equation given by Grimm-Temp to calculate infiltration rate. So what we are going to do is this. We are just going to take natural log here and we are going to simplify this equation in forms of an equation of straight line, that is linear equation. So what we are going to do, so if we do that, we'll get an equation something like that. F is equals to a plus b times of f of t. So what we are saying here is a is nothing but k and b is nothing but product of k psi delta, and we are supposed to calculate these values a and b, right? So we can say that a here is k and b here is k psi delta theta. Since we don't have values of these terms, that is k psi and delta theta, so we have just replaced them with a and b. We know the value of f of t and we know the value of small f. Now what we can do is we can give the values and we can solve simultaneous equations. Since we have multiple values, right, the equation, if we fit this equation, the equation will be a straight line. So instead of plotting, what we can do, we can take randomly any 2 points. Since the equation of this thing is a linear equation, so we can take any 2 points and we can substitute in this equation and we can get the value of a and b. So let us do that. If we substitute the value of small f as 3.6 times of a plus b and capital F of t as 2.2, this is equation 2, and next value we are taking is 2. Let us take 1.3 a plus b divided by 9.1, this is 3. Now if we solve these two terms, we'll get the value of A and B. So if we solve them, we are getting the value of A as 6.637 and B as 0.566. So if we compare A, we know A is nothing but here A is equals to K, means the value of K we get here. The value of K is 6.673 centimeter per hour. That is hydraulic conductivity. We got the value of K. Similarly, we want to calculate the value of other variables. So the other variables, how we can get this? E is nothing but psi K delta theta, right? And we know the value of K now. So from that, and also we know the value of B. B is nothing but 0.566 psi, value of K is 6.67 and that is delta theta. So from there we can get the value of psi delta theta. And once we get the value of psi delta theta, we can get the value of we got the value of K, and we got the value of B. So they have asked us to determine the value of A and B. And also in the same equation, if we want to calculate the value of small f, so how we can do that? Small f is nothing but k psi delta theta by f, right? So we know the value of k, we can substitute that value here. We know the value of k psi delta theta now, we can substitute that, and we know the value of capital F. Now this is the condition for 6R, right? And they are asking us, because in the equation they are asking us what would be the value of infiltration rate and cumulative infiltration at 6R, right? So at 6R we need to calculate, so we know these values now. We want to calculate F, so we need, if we want to calculate value of small f, we need to get the value of capital F here. So first we can calculate capital F. So the equation of capital F is Kt times capital F minus psi delta theta natural log of 1 plus f of psi delta theta, right? This is the equation to get the value of f. So here we can put the value of t as 6 hours. We can substitute the value of k which we got above, something around 6.67. We got the value of psi delta theta also. So all these terms are known to us now. So the only thing that is needed to be calculated is capital F. So from here we'll get the value of capital F, which will be coming around 11.33 centimeter. So we got the value of cumulative infiltration at 6 hours. So now this value we are going to substitute in equation above, this equation, and then we can get the value of small f. Value of small f is coming around 1.154 centimeter per hour. So this is one example of how you can use Grimmt equation and you can calculate the value of cumulative infiltration as well as infiltration rate. Also whenever we are talking about empirical equations, right? So the first empirical equation that we talk about, or which we remember, is Horton's equation. The second was Kostiakov's equation. And the third was Phillips. Like Phillips is a theoretical equation, but I am taking here only. So just remember, whenever we are solving this equation, you should remember their detailed form, and later you are going to convert their detailed form into a linear equation in the form of y is equals to mx plus c. What does this mean by, like if you look at Horton's equation, the curve, the equation of like the curve is something like that, right? The parameter here is infiltration rate, this is the value of f0, that is initial. Now this is the value of f of c, this is time. So what we are going to do this, we are going to convert this graph in terms of equation of straight line, just to just so that we can get the value of unknown, that is f of fc and k, in a simplified form. So just make a note of all this equation on your own. It would be useful for your final examination as well. You need to have a ready-made equations, a ready-made set of equations of all the empirical equations into a simplified linear equation. That would be helpful for you to solve any equation based on empirical equation to calculate infiltration rate or cumulative infiltration. So this is everything that was there to be discussed in today's class, that was about subsurface water, right? So in the next class, I think we'll be talking more into about ponding time, and then we'll be going into about surface phenomena, that is surface runoff. So in the next week, we'll talk about more about ponding time and surface runoff. In this week, we have covered everything which was to be covered on the topic of subsurface water, where we discussed about a hydrological process which is called as infiltration. We discussed about the definition, the factors, the different representation of infiltration, the relationship between cumulative as well as infiltration rate. Then we discussed about how to calculate actual infiltration if we know the value of infiltration rainfall intensity and uh, potential infiltration, right? We know that two cases. Then we talked about how infiltration can be measured. So with the help of instrument, that is infiltrometer, we studied how to record infiltration there using single ring infiltrometer as well as double ring. Then we looked into estimation of infiltration based on empirical equations. So we covered two empirical equations and we covered two theoretical equations. Then we have taken numerical based on each of them. We have taken equation on kostiakov's, we have taken numerical on Horton's equation. Then we have taken equation on Phillips, and at the very end we talked about green depth equation, and we have taken a small numerical also. So this is everything that was there. Then also we discussed few of the examples from the assignment, like how you can do. I've given a brief idea. So we still have time to submit the assignment. So you can look into this today's session and you can revise from it, and you can solve the assignment and submit it before the time. So this is everything for this week, and I hope you got few idea how to approach numericals on infiltration by today's session. And we'll meet in next week with week 6, and we'll talk more into the next topic, which is surface water.